Hello everyone, this is topic 8 and 9 for exam 2, our final two cases for integration by parts. First situation where both factors are cyclic, and then we look at inverse trig involved. But if you recall, the cyclic factors are e to the kx, sine of kx, and cosine of kx. So we referred to them as being cyclic with regards to repeated differentiations or integrations. They come back to themselves. And so if both factors of the integrand are cyclic, last time we saw one factor was cyclic and one was a polynomial, and we used the tabular method. But here, if both factors of the integrand are cyclic, then the original integral is going to come back to us. It'll reappear. And that will be after two applications of the integration by parts formula, as is mentioned in a little remark. Because if you imagine the situation in this example, no matter which one you choose to be u and which one you choose to be dv, that is, choose u to be e or choose dv to be sine, or vice versa, choose dv to be e and u to be sine. What happens is e, when differentiated or integrated, is going to come back to itself as e immediately. Sine is going to change to cosine, but then one more application, one more differentiation or integration is going to bring us back to sine. So two applications of the integration by parts formula, e goes to e and it stays as e, just modified by constants. Sine goes to cosine but comes back to sine. So this original integral is going to come back after two applications of integration by parts. And with that in mind, this is kind of a special case, but it does appear in many situations. With that in mind, I call integral I, uppercase I, for integral. And you'll see why I do that as we progress through the solution. So we're going to start as normal. Okay, you should notice that this requires integration by parts, and classify the factors. E is exponential, sine is trigonometric, but moreover, it's e to the kx, so it's cyclic, and it's sine of kx, so it's cyclic. So you have to know that this is the special situation where both factors are cyclic and the original integral comes back after two applications of integration by parts. I'm going to begin with line. Line 8 tells us to choose u between exponents. So we'll pick u to be 3x, and v is with the 4x. The difference. We have a little bit of cosine 3x, but we know times 3. So that's why I left the space in front in the differential dx. Okay, integrate dv to get v. That's our e to the kx formula. So 1 over 4 e to the 4x. And then the integration by parts formula. U times v minus the integral of v du. So we now have that what I'm calling this integral I is equal to u sine of 3x times v 1/4 e to the 4x, and then minus the integral of v 1/4 e to the 4x times our du, which is 3 cosine of 3x times the differential dx. Alright, now we'll take a step and clean things up a little bit. So this integral I is equal to, put the coefficient first. Remember, product of exponentials and trigs, we prefer them in that order. Exponential factor first, trigonometric factor second. And then we have minus, and from the new integral I want to factor out the 1/4 and the 3. So we'll have minus 3/4, and then the integral of, again, the exponential e to the 4x, and then the trig cosine 3x dx. Okay, so what's happened, as we could see, is what we expected. That is, one application of integration by parts, and we'll look at the new integral. This first term is part of the solution, so we're done with that. But one integration by parts and this same x. As you can see here, my computer froze. So e stayed and sine became cosine. So therefore, if we apply integration by parts to this new integral, we would expect that e would stay and cosine would change back to sine, and we'll have the original integral. So that's our plan. We'll still be consistent with y8. We can call e again the exponential, and cosine the trigonometric with regards to what our integration by parts choice of u and dv. So u will be cosine of 3x, d 4x dx again. Okay, this is going to be, alright, derivative of cosine is minus sine. I'm going to write the minus, I'm going to leave a little space in front because it's minus sine of the same argument, and then the derivative of the argument, which is 3. So I'll put that in front, and then the dx. Integrating dv to get v again, we get 1/4 e to the 4x. And then we have u times v minus the integral of v du. Okay, so now we have that this integral I is equal to, again, this first term just gets recopied. 1/4 e to the 4x sine of 3x. But now here's something very important. We saw this in the last situation as well. When we have this negative 3/4 here, that is the coefficient of this integral. And we are about to apply this integration by parts formula to that new integral. And that will generate two terms. So therefore we need parentheses, brackets, some types of grouping symbols, unless you want to mentally distribute, of course, to indicate that the negative 3/4 needs to be distributed to the two terms that are created by using our integration by parts formula. So the integration by parts formula, u cosine 3x times v 1/4 e to the 4x, and then minus the integral of v 1/4 e to the 4x times our du, which is minus 3 sine of 3x, and differential dx. And close up the brackets. So now we have that the integral I is 1/4 e to the 4x sine of 3x. So again, just recopy that. But this negative 3/4 needs to be distributed. So multiplied by this one, 3/6. We've got and I prefer that to 4x, 3x. Now here you got to be really careful, because at the same time that we distribute this negative 3/4, we're going to quarter, and this, which would be quarters. But then don't forget as well, negative 3/4 times this 3/4 would be negative 9/16. And then we have the integral of e to the 4x sine of 3x with respect to x. Okay, so now what's happened is what we expected to happen. After two applications of their formal integration by parts formula, this original integral came back to us. And so just modified by this coefficient of negative 9/16 in this case. Alright, so what we're going to do, and this is the reason why I called it I, because we've got to solve for this integral. So I'm going to replace that by I, because that's what it is. That's what we called it, I. So instead of having to juggle around the integral and rewrite it many times on the left-hand side here and then in subsequent steps to finish this off, it's convenient to call it I, as I've done. You don't have to. You could rewrite the integral if you want, but I feel it makes it easier, makes it stand out as a special problem, and then it's going to help us in the end here, as we're going to see. Now these first two terms are finished, so I'm just recopying them, and all I'm doing in this step is replacing the integral by I. So we have the first two terms recopied, then minus 9/16 I. And now what we need to do is solve for I. And don't make this harder than it is, because all we're doing is solving a linear equation, basically. We're going to get all the i's on one side. So 16. And on the left, we're going to need a least common denominator, which is 16. So we got 1i plus 9/16 I. Treat that as 16 over 16i. And we get 25 over 16i. And that's equal to, then we're just going to recopy. And I'm going to leave a little space in front. We'll just recopy the 1/4 e to the 4x sine 3x minus the 3/16 e to the 4x cosine 3x. And to solve for I now, the reason why I left the little space in front there is because we can think of dividing out 25 over 16, but that's kind of cumbersome. More efficient to think of multiplying by its reciprocal, 16 over 25. So on the left, everything cancels. We just get 1i over 1, or just I. And on the right, what we'll do is we'll distribute this 16 over 25 and multiplied by the first term. 4 goes into 16 4 times. So 4 over 25 e to the 4x sine 3x, and then minus distributing the 16 over 25 times 3/16. The 16s cancel, and we get minus 3 over 25 e to the 4x sine of 3x. And that's what the integral is equal to. Now, that'll get you, this is a 10-point problem on the exam, that'll get you 9 out of 10 points, because actually we're missing something. This is an indefinite integral, so please include the constant of integration. It would hurt me deeply to have to take off a point if you go through all that beautiful calculus and forget the constant. But, good news, we can actually use an approach rather than going through this the formal way. I wanted to go through it the formal way once with you so you could see the theory unfold on how it came back, the integral that is, after 2 applications of integration by parts. But there's actually an easier way, and that is to use what I'm calling the modified tabular method. So here's an example, and I made a note at the top where if both factors of the integrand are cyclic, we can use what I'm calling a modified tabular method. So this is the approach, as you're going to see, that I want you to use. Okay, you don't have to do it the long way. This is the way I want you to do it. Recognize that it's the special case. Both factors are cyclic in the form of an exponent form, each is cyclic, which is cyclic as well. So now we know that the original integral is going to come back to us after iteration of the formula. And so, like we did in the last example, I'm going to call this integral I. But now, instead of saying u equals and dv equals, we're going to have a column, because we're going to use the tabular approach. We're going to have a column labeled u and a column labeled dv. And we'll be consistent with y8, like we were in that last example. And we'll choose our u in that order. In particular, trig precedes the exponential. So I'm not going to say u equals, right underneath my u, I'm going to put the trig, cosine 3x. And I'm not going to say dv equals, just right underneath the dv column, I'm going to write the exponential e to the 2x. Remember, with the tabular method, we don't include dx or anything. And we don't say u equals and we don't say dv equals. Now here's why I call it the modified tabular method. It is because in the previous situations when we used the tabular method, u was a polynomial. And we were able to differentiate that polynomial successively to get 0. Now, you'll never be able to differentiate cosine to be 0. It just keeps bouncing back and forth between sine and cosine. But as we said, 2 applications of integration by parts should bring back this original integral. So therefore, the reason I'm calling it modified is because we're only going to differentiate twice and integrate twice. Now make sure you put yourself in the proper mode. The derivative of cosine is minus sine. So I'm going to write minus, I'm going to leave a little space, sine of 3x. We don't put the dx, but we do need the derivative of 3x, which is 3. And that's what I left the space out in front for. And we'll differentiate one more time. Derivative of sine, positive cosine. So this stays negative. Leave a little space for the new coefficient. And the new coefficient, another factor of 9. And we'll write e to the 2, the same again, just twice. And so integrating the 2 e to the 2x once, we get 1/2 e to the 2x. And integrating, we get another factor of 1/2, so 1/4 e to the 2x, and we stop. Only 2 times. Now the integration by parts tabular method says first entry in the u, second entry in the dv column, next diagonal, then the horizontal. We alternate